Good morning, class. This is practice test number 3, covering chapter 6 and 7. Chapter 6, normal probability distribution. Chapter 7, estimating parameters and determining sample sizes. And here's chapter 6, normal probability distribution. We're going to look at the first half of that. So we want to answer the following. What percent of a normally distributed data value lie within 2 standard deviations to either side of the mean? It's about 95%, the empirical rule that we have discussed before, but let's delve into it with more details. This is a normal curve, which is bell-shaped, and it's symmetric with respect to the value of mu. The formula is pretty complicated. The function that represents this bell curve is e to the power of minus the parentheses x minus mu quantity squared over 2 sigma squared over sigma over square root of 2 pi. This happened to represent the normal curve, where e is 2.718, pi is of course roughly 3.14, mu is the population mean, sigma is the population standard deviation. Another way of representing it would be in this format, and the result is that it's symmetric, so the total area represents the total probability, and it's equal to 1. And on each side, so the total area is 1, and on each side we have the area equal to 0.5 by symmetry. Each side has the area of 0.5. The normal distribution, or short ND curve, is bell-shaped. The mean, median, and mode are all equal and located at the center. The curve is symmetrical about the mean, mu. The curve is continuous, i.e. there are no gaps or holes. The curve never touches the x-axis. It continues indefinitely on both sides towards positive infinity and negative infinity. It goes from negative to positive infinity. The total area under the curve is 1 or 100%, which is the representation of the total probability. And as I said, on each side is 0.5. This is the empirical rule that we have seen. The area under the normal curve that lies within 1 standard deviation of the mean is approximately 68%. So within 1 standard deviation, just for the sake of argument, means this part. The area under the normal curve that lies within 2 standard deviations of the mean is approximately 95%. So we add this part also. So from here to here, mu minus 2 sigma all the way to mu plus 2 sigma. So for the second case, we are looking at the blue one. Number 3 is if we go with 3 standard deviations over, here's mu, subtract 3 sigma from it, so mu minus 3 sigma, add 3 sigma, so it covers almost everything. It covers 99.7%. So 3 standard deviations of the mean is approximately 0.997 or 99.7. That's the general concept. Now, as far as the normal distribution, in this case, when we want it within 2 standard deviations, that means z is 2. So p of negative 2 to 2, z is between negative 2 and positive 2, which means p of 2 minus p of minus 2. That means we figure out what is the probability from negative infinity to positive 2. That means this part. And then we figure out what is the probability from negative infinity to negative to this part, we subtract from it. And when we look up these values from the table, 0.972 minus 0.0228, we get 0.9544. It's about 95%, but more precisely, 95.44%. This comes from the Z table, okay, in the concept of a normal distribution. So it comes from the Z table, or you can use technology to get there. Either way is fine. Let's move on. So we're going to continue with the first question, part B. For a continuous random variable, the probability of a single value of x is always 0. The reason is a single value does not cover any area under the curve. Remember, the total probability is the total area under the curve. So to find probability, you have to find the area, and a single value does not cover any area. The parameters of normal distributions are mu and sigma, the mean and standard deviation, the mean and standard deviation. What are the values of mean and standard deviation for the standard normal distribution? This we call it for short SND. Mu is 0, sigma is 1. And this is the concept known as the Z-score. Z-score refers to a normal distribution with mu being 0, sigma being 1. SND, standard normal distribution. SND, standard normal distribution. We want to find the Z value, the value of Z, for a standard normal distribution, SND, such that the area in the left tail is 0.05. It's always a good practice to graph, even if it's not to scale, but the idea is that it's a normal curve, and you want this area to the left be 0.05. And remember, this corresponds to mu or Z equals 0. So right here, corresponds to Z equals 0, okay? Let's look at the table. When you look at the Z table normally represents the area from negative infinity to the value of Z, okay? And we want the area to be 0.05. On the left column and the top row, we can find the Z values. For example, this one would be minus 3.51, okay? Since we want the area, we look at the body here. So if we continue, we are looking for number 0.05 in the body of the table, not on the side. These are the Z-scores. So take a look at what happens. 0.05 doesn't exist. So we find two numbers such that 0.05 is in between. So over here, we have negative 1.6. Over here, we have the two numbers. So this corresponds to negative 1.64. This 0.0495 area corresponds to negative 1.65. So to go in between these two numbers, between negative 1.64 and negative 1.65, we are going to say negative 1.645. We're going to go with it. So negative 1.64, negative 1.65, in between is negative 1.645. So again, I want to make sure we see that this means 1.64. This means 1.65. We want the number in between. In fact, if you look at the table with the asterisk, it shows you that number, negative 1.64. Now, this is using the table and the concept of a cumulative area from the left. Cumulative area from the left. That's why I showed you this. Now, you can use a calculator. For a TI calculator, you go with second variables inverse normal, and you put 3 enters left area, value of the mean, standard deviation, and so in this case, the area is 0.05, mu is 0, sigma is 1, and that gives you, of course, the number that is a lot more precise than this one. But if you go with the third decimal, 4 is the third decimal, next to it is 8, it goes up to 5. So when you do the rounding, you do it accordingly. So next to 4 is 8, it goes up to 5. So that's fine. You could use some calculators online, for example, this one, and you can see it in MOM. I have put a lot of calculators. You can use Excel, which uses basically a similar command, or you can use any technology of your choice. So we're just discussing normal distribution and tables. Now we want to find the value of Z for a standard normal distribution such that the area in the right is 0.1. And remember, this is the cumulative area from the left, and this is the area we want, 0.1. And by the way, you do have the positive Z value, negative Z value in the tables that I've posted. If this is 0.1, and to do the reading from this table, we need the area to the left, which is 1 minus that, or 0.9. So this area is 0.9. So we are going to go to the body of this table and try to find 0.9. It doesn't exist, but 0.9 is between these two numbers. So this corresponds to 1.2, 0.08, 0.09, which means it's somewhere between 1.28 and 1.29, and we say 1.285, somewhere between the two numbers. If we were to do it by the table, and the table is fine, perfect. Technology, of course, gives you a better answer. If we want to go with the technology, we write inverse norm with the area 0.9. We want the area to the left. Mu 0 sigma equals 1, and it results in this number. Of course, you might say they are off. Well, with two decimals, they are the same. If we go with the third one, this changes to 2, becomes 1.282, because next to it is 5, which is not the same as that one, because this is, of course, a lot more precise with more decimals. Find the probability of a Z being larger than negative 0.82. Well, here's the table, and graphing is a must. It really helps you see. So you want the probability of Z larger than negative 0.82. This is 0. On the right side is positive number, on the left side is negative. And by the way, you talk about the area. I don't know the answer, but for sure it's larger than 0.5. That's the idea that will help you with the graph. So in order to find that, you can find this, okay, area from the table, because it gives you the cumulative area from the left, and then subtract it from 1. So with that being the case, if you go down, we are looking at negative 3.4, negative 3.3, and there is not enough space. So I grab the negative 0.8, and I want negative 0.82. So I want this one and this one. If we put those two together, results in 0.2061. So that's the green shaded region. To get what we want, we're going to subtract this number from 1, which gives us 0.7939 or almost 0.8. Sometimes students make a mistake. They don't remember to do the rest and they report this as that. The graph will help you see that the answer must be larger than 0.5. Now, by symmetry, if you look up z equals 0.82 by symmetry, in other words, the probability of z less than positive 0.82, these two give you the same answer. They don't refer to the same thing, but the area under the curve for z larger than negative 0.82 and for z less than 0.82, they are the same class. Okay, so again, the point being, they may not refer to the same thing, but it's important to see that they give you the same answer. And that is extremely important to understand. Sometimes it makes it easier to find that. So with that being the case, we can go with technology. The lower, now here's what I want you to understand. The lower is negative 0.82, and it goes to infinity, everybody. As far as the z table is concerned, within 3 standard deviation, we cover 99.7%. So after almost, after like 3.5, they consider like point with 3 zeros and 1, or before negative 3.5. So if you use a large number, and 1,000 is large, some people use 10,000, some people just use 100. That's good enough. Please pay attention. This is just your choice, but it goes to infinity. Just pick a number, 100,000. Believe you me, 1,000 will give you the answer, and you can try it. Change this to a number larger than that. It doesn't change much. So this one, of course, if we go with 4 decimals, 1, 2, 3, 4, number 8 is the fourth one. Since next to it is 9, I have to change this to 8 plus 1, 9. So within 4 decimals, they are identical. Okay, so the table does a pretty good job. But again, I want to make sure we understand why we use the upper as 1,000. This goes, when we say z is larger than minus 0.82, this goes to infinity. The z-value for mu is always, for any normal distribution, is 0 class. Why is that? Because z is x minus mu over sigma. Replace the x with mu. That's the proof, actually. Usually, the normal distribution is used as an approximation to binomial distribution when NP and NQ are large. How large? In some texts, they go with 5, but in some texts, including mom, they go with 10. When NP and NQ are large, that means they are larger than or equal to 10. Find the area of the shaded region. Okay. The graph depicts the standard normal distribution of bone density score with mean of 0 and standard deviation of 1. So mu is 0, sigma is 1. That means basically standard normal distribution, and we want the probability of a z larger than negative 0.93. Again, I don't know that. I got to look up the table or go with the technology, but I do know it's larger than 0.5 because half of it is 0.5. Okay. And so if you go with technology, normal CDF, you put negative 0.93 with mu being 0, sigma being 1, and it gives you this answer. And if you go with 4 decimals, after 8 is 1, so 8 remains unchanged. So I'm using a TI calculator. Okay. By the way, I'm saying for negative infinity, you can use minus 1000. For infinity, you can use 1000. Pay attention to what I wrote here. The graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So mu is 100, sigma is 15. That's the given information. And we want the probability of x between 106 and 132. So we can use z equals x minus mu over sigma and evaluate the z score, meaning we go from normal distribution to standard normal distribution. So z is x minus mu over sigma. Mu is 100, sigma is 15. What is x? Put 106 and it gives you 0.4. Put 132 and it gives you 2.133. So the probability of z score between these two values. So this is normal distribution. This is standard normal distribution. So let me class, this is normal distribution. This is standard normal distribution, z score. And you can look up the table. You can go with the technology. If you go with the table, it gives you two values. I'm assuming by now everybody can figure out how to look up the table, or you can use the technology, and you end up with one of those values close to 0.3280 or 0.3281. Either way is fine. We are going to move on. Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Find the probability that a given score is between negative 2.13 and positive 3.77 and draw a sketch of the region. So clearly, mu is 0, sigma equals 1 in essence is just like the standard normal distribution or z scores. And the graph looks something like that. Again, it doesn't have to be to scale. So we're going to go from negative 2.13 to 3.77, and this is the region of interest. So this is what we want. And all you have to do, use technology or use table to come up with the answer. Again, writing this is extremely important. Graphing this is extremely important. Now, you can use the technology. So the lower value for normal CDF, cumulative distribution frequency, cumulative distributed frequency. So minus 2.13. And the upper is 3.77, mu 0, sigma is 1. And if you put it in, it results in this number. And if you go with 4 decimals, 0.9833, next to 3 is 3, so it doesn't change. Okay, because this is number 3, this remains unchanged. So when you do the rounding, you must do it accordingly. Draw a graph and find P19. What is P19? The 19th percentile. This is the bone density score separating the bottom 19% from the top 81%. Bottom 90% from the top 81%, which means we are looking at this graph. So this whole area is 1, the area is 0.19. And this represents P19. So we are going to find the z-score for that and take it from there. Because mu is 0, sigma is 1, all you have to do find the z-score for that. Otherwise, you would go to x. Z equals x minus mu over sigma. We will look at that concept later on. All right. So from the table, if you use the table, when area to the left is, and we don't have 0.19, when it's 0.1922, the z-score is negative 0.87 from the table. When it's less than 0.19, 0.189 for z is negative 0.88. That means we don't have this number, but we have this number between these two. You see that 0.19 is between 0.1894 and 0.1922. Therefore, the z-score is between these two, minus 0.87, minus 0.88. So we're going to say minus 0.875. This is closer. If we were to choose one of those from the table, we would go with that. But we go in between. Let's look at the technology. So inverse norm, area is 0.919, and mu is 0, sigma is 1. And that results in negative 0.877896, and it continues indefinitely and depends where you want to stop. If you want to go with 2 decimals, you get negative 0.88. If you go with 3 decimals, negative 0.87. Now this 7 changes to 8 because next to it is 8. So 0.878, a little bit different than what we have. But remember, technology obviously does a better job. And again, if you wanted to go with the no Excel, you go normal CDF and you put 4 entries, the left bound, right bound values of the mean and standard deviation. And again, for negative infinity, use negative 1000. For positive infinity, use positive 1000. Three out of 8 drinkers acquire the habit by age 20. If 300 drinkers are randomly selected, use normal approximation to the binomial distribution. Find the probability that exactly 100 acquire the habit by age 20. Well, this is clearly a binomial distribution because either one gets to the habit or not, with n being 300, p being 3 out of 8 or 3 over 8. So it's a binomial distribution. Anytime you claim it's a binomial distribution, you must write n and p. So if we have that, then let's go with the formulas for a binomial distribution. Remember, P of x is n factorial over x factorial, n minus x factorial, p to the power of x, q to the power of n minus x, mu is np, sigma is square root of npq, q is 1 minus p. So basically, we need to know q, this is p 3 over 8, and q is 1 minus that. So if we were to use this formula, we can plug in, and of course it requires a calculator to come up with the answer. And because NP and NQ are large, we can use normal distribution as an approximation. The question is, how do we use that? So I want to go over this concept. Again, we could use for this one, just replace the N and P and Q, and X is 100. You can come up with the answer using the formula. Binomial distribution, we want probability of X equals 100. For normal distribution, we are going to understand that for normal distribution, if I use 100, I get 0. Why is that? Because binomial distribution is discrete, normal distribution is continuous, and a continuous random variable, when you want to find the probability of a single value, is 0. We've discussed that. So you need to make up an area. So statisticians have decided to go 0.5 to the left and right. So we're going to add and subtract 0.5. This way it creates an area. This is called continually correction factor. Okay, I will discuss that in the next page again. But basically, we add 0.5 to create an area. That's really the bottom line. Okay, and why 0.5? Normally doesn't change that much. You can go with 0.1, but statisticians have decided to go with 0.5. So now the next step is to go to standard normal distribution. To go to standard normal distribution, z is x minus mu over sigma. So let's calculate the z-score for this and this. To do that, we need to use z equals x minus mu over sigma. We have the x. We have to calculate mu, which is np, and sigma, which is square root of npq. So mu is the product of these two, np. Sigma is square root of npq. So we have to calculate both of them for the sake of the z-score, everybody, which is x minus mu over sigma. So for 99.5, we get 99.5 minus mu, which is 112.5, divided by sigma. You want to carry out a lot of decimals because you want to come close to a precise answer. And the left side, 99.5, corresponds to the z-score of negative 1.5503. And the right side, 100.5. So now 100.5 minus this over this, that corresponds to 100.5 here. And now we go from normal distribution to SND, standard normal distribution. So 99.5 corresponds to negative 1.55, 100.5 corresponds to negative 1.43. Using the table for this number, okay, so this is the graph. It's really interesting to see that how we do the graph. It's really good to always use the graph, everybody. Okay, use the graph because it will help you see in case you do something wrong. So from the graph, we want to go all the way to negative 1.43 gives us 0.0764, all the way to negative 1.55, negative the area of 0.0606. Subtract this area from this area, and it gives us 0.0158. If we were to do this in this manner, I want to make sure we understand what happened. Binomial distribution. We add and subtract 0.5 to make it continuous and therefore normal distribution. We calculate the z-score to go to standard normal distribution. And here's from the table. Here's from the table, everybody. Okay, that's fine. Let's do technology. Normal CDF from this number to this number, of course, with a lot more decimal, right? If you plug in to a calculator. And it gives you this value. This is using a normal CDF. This is using normal CDF with a table. This is using it with technology. And going back to binomial distribution, if you go binomial PDF, N is 300. P is 3 over 8 or 0.375. X value is 100. Take a look at what happens. This is the value we got from the technology for normal CDF. This is the value we got from technology for binomial PDF. And this is the one we did from the table. As you can see, within 4 decimals, 1, 2, 3, 4, this 7 has to be changed to 8, right? Next to this 8. 1, 2, 3, 4, this 7 has to be changed. As you can see, they are identical within 4 decimals. And these two are slightly different again because it's an approximation for a binomial. Why did they do that? Now that you have the technology, you don't have to really worry about it too much. But when they didn't have the technology, it was very tough to calculate this, and they would go with the normal distribution as an approximation. We are looking at the same question. Part B, at least 125 acquired the habit by age 20. We are looking at the same question, which was a binomial distribution with n being 300, p being 3 over 8 or 0.375. Q would be 1 minus that of 0.625. We have already calculated it from the previous page. Mu is 112.5, sigma is 8.3853. All right. So what do we want here? We want the probability of x larger than or equal to 125 binomial distribution, BD. What does it mean? Let x be 125, 126, 127, all the way to n, all the way to 300, everybody. That's the meaning of it. So we are going to go with the normal distribution. So we need this 0.5 continually correction factor. And I'm going to go over that in a moment. But before I go over that, I want to make sure we can figure out whether we need to add or subtract 0.5. Well, let's do both. If I add 125, if I get the probability of x larger than 125.5, please understand, in the case of a normal distribution, which is a continuous random variable, the endpoint is not important because one point, only 1 point, the probability is 0. So when we say larger than or equal to 125.5, even if I put the equality, and I'm going to put it with a different color, doesn't matter. Okay. Now, when we say larger than 125.5, and we have to go with a binomial distribution, discrete value, the very first number that is discrete is 126, 127, and all the way to the end. So what happens? I lose the first entry. However, if I change this to 124.5, what happens? Well, larger than, so I want larger than 124.5. That is going to give me probability of x equals larger than 124.5. 125 plus 126 all the way to the end. And this will not lose the first one, which is 125. This is the one I'm going to use. So I don't want you to memorize. In this case, we add 0.5. In that case, we subtract 0.5. Put both of it. Put 125.5 as well as 124.5, and look at the very first number that comes after that. If you put 125.5, the very first number that is a whole number is 126. In this one, the very first number is 125. Since we need 125, then this is no good. Okay. Now I want to discuss this continually correction factor and the meaning of it. Could somebody read this continually correction factor? Go ahead. Or continuity correction factor, either. Go ahead. Somebody read that, please.
Use a continuity correction factor of 0.5. The continuity correction factor is applied when a continuous probability distribution is used for approximating a discrete probability distribution. Acts like a bridge between the continuous normal distribution and the discrete binomial.
Excellent, thanks. So that's why we use the 0.5. Let me clean up. Now what happens? So we went from binomial distribution to normal distribution. The next one is SND. How do I go to SND? I have to calculate the z-score. X 124.5 minus mu 112.5 over sigma 8.3853, and that results in 1.4311. I put it here. So I went from binomial distribution to normal distribution to standard normal distribution. Okay, very straightforward, everybody. And now, table, technology, you name it, you come up with the answer. So it's really a good idea to graph just because you should know it's clearly smaller than 0.5 and it's pretty small. Okay, remember the entire area is 1, each side is 0.5. So from the, if you go from the table, you find this area because the table gives you on the left side, right? The cumulative value on the left side. So you find this area and subtract it from 1. So this is clearly from the table, 1 minus 0.9236, it gives you up to 4 decimals, and the region is 0.0764. So the probability that at least 125 acquired the habit by age 20 is 0.0764 or 7.64%. Depends on how they want it. All right, let's move on. We are looking at the same question. 3 out of 8 drinkers acquired the habit by age 20. Now, what is the probability? Find the probability that at most 165 acquired the habit by age 20. Again, the same situation from the previous pages. The N, P, Q, mu, sigma, all of the above. So we want binomial distribution, probability of x less than or equal to 165. What does it mean? Probability of x equals 165 plus probability of x equals 164 all the way to 0. That's what we want. So clearly, by hand, it's horrible because you have to calculate each of those binomial distributions, but we are going to go with the normal distribution. To go with the normal distribution, we have two choices. We can change this. Remember, we have to either add or subtract. So we have two choices. We can say probability of x less than 164.5 or probability of x less than 165.5, one of the two. So I'm going to call it number 1, number 2. Which one are we going to use and why? Well, all you have to do, look at the very beginning. We need this one. Any of them that gives us the first one, we are fine. So I hope you see that this one gives you P of 164 as the first one, and it goes all the way to P of 0, right? Because we say x is less than 164.5. But the second one, less than 165.5, the first discrete number, whole number, is 165, and it gives us what we want. And therefore, for a normal distribution, we are going to choose probability of x less than 165.5. To go to standard normal distribution, we are going to go with the z-score x minus mu over sigma. We have mu and sigma here. What is x? 165.5, ending up with 6.3206. So probability of ND and now SND, probability of Z less than this number. Now, if you go, it's a good practice to go with the graph. So somewhere here. Okay, this is obviously not to scale. So 6.3206. So you want this area. And I hope you see that if you said it's 1 or almost 1, you're absolutely correct. As far as the table is concerned, when it's above 3.5, when the number is larger than 3.5, from negative infinity to 3.5, they use 4 decimals, 0 point with 49, 0.9999. But if you use a technology, it's different. And that's why you have to carry a lot of decimals, because it's extremely close to 1, but it's not 1. So you want to be careful with that. So the answer is 0.9999 from the table.